we starting now?
Yeah, you should.
Okay, welcome everyone, all the enthusiasts of astronomy and all the lovers of physics here, and even our neighbors who, that we share a building with. So we are here, I guess. A unique event is going to happen on Monday, a solar eclipse, and we all are hyped because, well, I guess for the next one we'll have to wait for 20 years unless we want to fly, to other parts of the planet. And I guess what we're here for is to learn physically why it happens. I think Francine Jacobs is going to do that. And then we're going to hear about, I'm sure all of you know about these stories, how in ancient worlds they perceive this event. So all I remember from reading the books, how freaked out they are, gods are mad on us and we're all going to go crazy, right? It's the end of the world and all that stuff. But Angella Johnson's going to do a much better job than me. And then for the end of the program, my dear colleague Stephon Alexander will talk about enigmas of solar eclipse. Now, what he means by enigma, I don't know. He didn't tell me. So,
it's called Yandel Antonio.
Yeah. Without further ado, I'll call Francine here to show us all her gadgets that she has here. Yeah. Thank you.
One of them's yours.
Yeah.
Having come here. Has anybody ever seen an eclipse before? Some of you have, right? Are you leaving or are you staying here?
Leaving.
That's not too bad. Considering others that we've had. Now the next question. Anybody know who I am? 2 people. Thank you. Yes. Any of you read the lab notes? I am the lab note, if you will. And also, on behalf of Lab Observatory, I do a lot of public service, if you will. Several years ago, during the 2017 eclipse, I joined the Rhode Island Library Association. And one of the things that I did this year, or last year, is I said, well, I'd be willing to talk to libraries if they want to know about it. After I leave here, I will be going to my 14th library tour. The joys of volunteerism. And one of the major things that I do stress, of course, besides kind of giving a quick review of what they are and the history of it, is the safe viewing. And I have here a couple things, one of which I did not drag down from the 2nd floor, but if any of you are going to be in the green Monday, you'll probably see the H-alpha telescope. Some of you have probably looked through that. Basically one of the only safe, direct telescopes that you can observe the sun with. Now, otherwise, something that they will be having is something that I'm sure some of you have seen before, and this is one of my favorite little things here. This is a sun spotter, which looks very easy, but unfortunately is very expensive, so be thankful that Brown has a few of these. What it is the sun goes right through this window, and through the magic of mirrors, it ends up projecting down here. So you get to see the entire ball of the sun. Now, a couple good things about this. First of all, it's totally safe. You have no problems looking at it. And a lot of people can see the image at one time. You don't have to push somebody away from the telescope or anything. This is something that several people can really enjoy looking at. And you may think it doesn't look like much, but during the past 2 transits of Mercury, we were able to actually see Mercury cross the face of the sun with this little tiny. So it's a very nice, easy, compact, expensive piece of material. So, also, a couple things that, actually just one major thing that I've been concentrating on is the fact that a lot of people think that science equipment is very expensive. All agree? Mm-hmm. I have something that you probably all have in your homes, and and it works. Exactly. Yes, of course if it's going to be a hot day, don't use a metal one. But just with the sun behind you, let the rays come through here. Every single one of these holes will become a red, will show the sun passing right through, landing on the ground, and you will be able to watch the moon travel directly in front of the sun. So you will have dozens, depending on how many holes you have, or hundreds of solar images passing through. Now, if you don't want to do that, some of you probably know, all you have to do is kind of just take your fingers and wrap them together, and the holes between your fingers will do the same. Or, although it's not really happening this month, if you're under a tree with leaves, chuck that up. But anyway, if it gets to be warm. Now, one of the major problems, of course, is sun safety. And I understand that some of you already have them. But if not, they will be given out Monday. Is that correct? People that are here?
They'll be given out, but we will ask people to bring them back. We only have about 1,000.
You're not going to have them hold out till 2045?
I'm not sure I trust the integrity of something like that.
This is really the safest way, and quite honestly, the easiest way to actually observe. Now, we have been hearing, of course, that there have been some, shall we say, replicas, be very nice. There is, those of you that have them, there is a number here that tells you that these glasses have been approved, if you will, by all scientific organizations here. And one of the problems that I know some people are having is, they figure, yes, okay, the eclipse is over, but you can still observe the sun with this. So that's why, we call them eclipse glasses, but they really should be called safe solar viewing glasses. Because even when the eclipse is over, we can still use them. And if the sun is as active as we're saying it's supposed to be, this should be something really nice for them to observe. And I know someone had mentioned, how do we know that these are safe? One way, which I don't have with me, but do you have your phone with you?
I don't.
Oh, no. I left it upstairs. If you could put your flashlight on, please.
Oh, I don't have a flashlight, sorry.
I don't even have a phone.
How did that happen? Flashlight. If you can see the flashlight through here, you know that this is not a safe viewing. If you notice there's nothing here, these are okay. And with this, with all this stuff, I'll get out of the way. And I'm sure all of you know probably much better than you know me, Angella, who will be talking about the history.
Hi, everyone. Actually, I'm a little nervous because the real historian is Francine. So as I walked in and I shared what I'm going to go over, she's like, well, did you think of this? Did you get this? Did you get this? But I have Francine and I have Jan there and some others, right? Okay. All right. You want to see that? Okay, so I really like this image because it's an AI-generated image of an Antikythera. And I'm going to talk about how the Greeks use this. It's very complicated, actually, and I believe Jan and I think, Rick, you had a little contest or something.
So we're trying to get students to build a 3D printed version.
Right.
Oh my gosh.
So what I'm hoping is you'll get something from this. Now, like I said, I'm no way near an expert, but there's some books you can read. And you may have some of your own, that's fine. The last one, I actually did an interview with Jim Gates, and the last one is really about proving Einstein right. So the 1919 eclipse that proved Einstein right, that's what that book is about. Okay, so I'm also here to plug episode 7 of our Physics Fundamental of our very own Jan Del Antonio. I'm hoping you'll watch it. It's going to premiere March 5th. So Friday at 9, we're going to be premiering that video. And we had talked about it for a while, right, Jan? And then because the eclipse is, coming up, we thought this would be a good one. So please check it out. Okay, so I'm going to cover pretty much four parts of this world, hopefully. Like I said, I can't cover all. But as Vesna said, eclipses was viewed as omen, and people were very afraid. And if you think about it, put yourself 900 BC and all of a sudden it's dark outside. You're going to need to come up with some reasoning as to, are the gods angry with us? What's going on? And you'll see that there are a lot of myths of animals, actually, dragons and so forth. So I'm going to talk first about Asia, Africa, Europe, and the Americas. So first, Asia. And I just checked. So this is around 900 BC. So, and this is in China. And they do have a lot of documentation of this. So the Chinese believed that there was a celestial dragon that was to devour the sun. So in order to keep that from happening, they would beat drums and pots and so forth. Interestingly enough, and I probably have some Chinese here, so you can correct me if I'm wrong, but interestingly enough, I researched this, and that the word actually means to eat. So it goes back to that character, I should say. The character actually means to eat, and it's because it was believed the dragon was eating the sun, and that's why they couldn't see. It was dark. In Vietnam, similarly, they believed that it was a frog god, and they kind of hoped for the Lord Han to convince the frog to spit it out. So by praying to Lord Han, the frog would spit it out. They'd see sunlight again. They're happy. Okay. This also is in India, this myth. And like I said, you'll probably find more if you do some research, do some digging, go online, but you'll probably find more. But believe it or not, it's also in the Rig Veda. And at the bottom, I have an image of the actual Sanskrit of the writing. And this is dating back quite a bit, 1200 to 1500 BC. Okay, so going to Africa, I didn't find as much in Africa. I don't know if you have anything, Francine, but the Middle East definitely. So the ancient Egyptians, they're very much into astronomy. We're finding that even some of the pyramids, I don't know if you've heard of this, Jan or Stephon, that it lines up with the belt of Orion. Mm-hmm. Yeah, so they're great mathematicians, and they calculate, but they also had sun god, and they focus on this. And as you can see at the top, they had it in a papyrus and etched out. You can see the sun, that's one of the pharaohs. And they had this myth that there was a snake god that was attacking the sun, and now it's believed that that's the myth that they use to explain eclipses. Okay, Babylon as well. Astronomy flourished in Babylon, but in particular, Mesopotamia, but in particular Babylon, and dating back to like the 4th millennium BC. And you can see at the top the papyrus writing there, and at the bottom. So they pretty much were coming up with some explanation, as I said. But in 200, they were the first to discover the 223-month period of the lunar eclipse. So they were the first ones to actually come up with some sort of theory to explain it and predict lunar eclipses. Okay, going to Europe. I'm not sure why it's not. Okay. So one slide is missing. I'm so sorry about that. Okay. So that slide had to do with the Greeks. But what's most important here is this mechanism that was used. And they found this mechanism, this is the image of it, on the seafloor in some wreckage, and that was in the 1900s. And they found that it's actually a hand-powered Ori, and it was to model the solar system. And it was the first, as they believe, analog computer. It's very interesting. Very advanced cultures even though we're talking about, so many years ago. Now this I found because I was preparing this and I wanted to be thorough. So the Swedes are also, the Nordic cultures also had their myths, and they believe that there's a wolf god that was devouring the sun, as you can see in the bottom part there in the picture. And then that's how they explain what was going on. Now, I read a little bit about this. I don't know if anyone knows, but they can't prove, but they believe that Stonehenge was also, as you know, Stonehenge is pretty much a mystery, but they found that it lines up, and it could have also been used to predict solar and lunar eclipses. And as you can see in the picture on the W, your far right, that was an ideal place for viewing an eclipse. So there's still a lot more research that can be done here. Now in the Americas, the Mayans they were also another advanced culture, and they came up with, this is an actual calendar, if you will. They come up with a calendar, and on the end, at the far right, that's the Dresden Codex, which was supposedly what they used, the tables that they used to predict lunar eclipses. So that was their lunar table. And then Jan helped me with this one because I did not know that the Navajo, the Native Americans, also had a tradition and a way of predicting. And that's a carving, 800-year-old carving, I believe, was found in Arizona. And I have here a quote from a Navajo Indian who said that they believe it was just a sacred time to sit and to reflect. Like almost all cultures saw this as something significant, something profound. And then the last, which is, like I said, not the most thorough, but the 1919 is the eclipse, and I believe you're going to talk about that, Stephon, because this is what made Einstein a science celebrity. And it's, this is your area, so I won't go, I decided not to talk too much about it or go too much in detail, but I pretty much verify one of the essential consequences of general relativity. And that's the actual image from the 1919. Okay, so I just threw this in there in case, unfortunately it's not going to be, the path, the direction is not that close to Rhode Island, and that's why so many are traveling. But still, nonetheless, it is something major and something you want to go out and enjoy. So thank you for your time and attention. I need to introduce, I don't even think Stephon needs an introduction, does he? But anyway, it's my responsibility to do that. And I want to say that here it says he's a theoretical cosmologist, particle physicist, and he is also looking at string theory, in particular loop gravity theory. He is, if you're able to go to For the Love of Physics, he is a jazz musician. He has a love for jazz music. He's written a book on the jazz of physics. And he was also previously president of NSBP, and just all around an amazing scientist, right? Stephon, is that a good introduction? Did I do good? Okay, so Stephon is up next. Thank you.
So, I have to follow two amazing talks by Francine and Angella. And let me not do any more advertisement than this company needs. So, so I want to thank all of our guests, of course, staff in the physics department, and students and faculty. So yeah, I need to put this on full. I've gotten blind recently and play from start. Okay. Oh, you got to do it. Okay. He's going to take care of that. And so I think, one of the things I worried about, actually, when I was preparing this, is like I know nothing about the mythology, except that when I spoke to my colleague Jim Gates, he said, yeah, people were scared as hell about this thing. So I'm glad that you confirmed that. I could imagine, sitting down one day and just all of a sudden seeing the sun disappear and saying, okay, what's going on here? I need I guess, way
I looked
Pointer?
it up.
Okay, a pointer? There was a pointer? Here we go. All right, so let's begin. So yes, oh, you're gonna plug that in. What I'm gonna run you through is a little bit of, kind of explain a little bit about the physics underlying the eclipse and the many uses that the eclipse, not many, but one important use it was to advance science and the technology that followed from that. And, oh, why is it? Oh, the little advance, oh, you got it. Let's go backwards. Okay. Okay. All right, so again, some of this information came from a great book that Professor Gates was writing when he was on faculty here. So I remember just sitting at this dining room table while he was, writing the book, telling me some interesting things that he himself never knew about, and that's why we write books, actually. And I'm going backwards here. Okay. This is very counterintuitive. This means down means to advance. Okay. So eclipses have a story to tell. And the story I want to tell is, by the way, we're going to use some physics to explain this. So if I have two rotating bodies, like a moon and a planet, they interact gravitationally. But gravity also doesn't only just exchange, right, a line of force. It's exchanging orbital angular momentum, rotational energy, but also spin energy. So there's a spin-spin interaction that gravity also transmits. This actually means that if the moon is rotating, right, the rotation of the moon can stabilize the Earth tilted. And so without the moon, life would not be as we know it. In fact, it would actually damage a lot of the functioning of our ecosystem globally if the seasons were unstable. So the rotation of the moon and the gravitational interaction is very important. And I learned this from talking to a colleague who's supposed to know something about this, but I'm not an expert. I'm going to call on you to confirm this. But the story is that the moon is exactly at the distance from the Earth, such that it is exactly the right size to obscure the sun, which is 400 times, right, the radius of the moon, right? If the moon, in other words, if the moon was further away or closer in, right, it not only would it disrupt life as we know it, including ours, so there's a nice coincidence there for life, meaning the distance between the Earth and the moon and its rotation. But if the moon actually was further away, or significantly further away, there would be no eclipse, no total eclipses. I'm going to talk about that in a second. And the reason why the moon is at its distance is actually just a dynamical coincidence. I'll talk about that in a second. And according to this theory, which is the most popular, I think, accepted theory of how the moon formed, how it came into being, actually also predicts that the moon is actually slowly swirling away from the Earth, such that in 250,000 years or something, there will be no more eclipses. So we exist exactly as human beings at the time where we could actually experience the eclipse. Is that more or less correct? All right, you got him on record there? Take a picture of him shaking his head. All right, so I want to show you a little, by the way, I've stolen some cheap videos, okay, with corny sound effects. I mean, if you don't like that, close your ears, plug your ears in, and it might fall, and I ain't gonna make no videos, okay? All right. So this is a computer simulation, okay, that kind of shows how a Mars-like planet in the early Earth, at that time, I believe the temperature of the Earth was on the order of a boiling 3,000 degrees Kelvin, and Mars, type object collided with the Earth, and this kind of simulation shows how the moon was formed. So we have to, before we talk about eclipses, we have to talk about this moon. And for some reason, my video ain't playing. Did when you, yeah. I have a few videos, so I hope it. Oh, I see. So we gotta do it that way. Okay, so no way to get those videos? they were embedded.
We can go to, if you have a website.
I guess I can go online, yes, go online. Okay, looks like we'll have to disrupt that. Okay, here we go. I think it's important to show nonetheless. Obviously the big one is the Earth. It's very hot, so that's why this is happening. That's what turns the moon, the small one, right? The other one just collapses back into the Earth. Thank you, NASA. Okay, you got me back on so far? We might have to do this for another one. It was one important video, but yeah. The next one will be an important one. But, all right, so, okay, now that we have our moon, and it's exactly the right distance, okay, obviously, you can see my shadow, right? We have light. Oh, here's my shadow. Right. That's exactly, in a sense, what we have light there, right? I'm obscuring the light, and therefore there's a shadow casted on it. And so effectively, I mean, more or less, that's what the moon is doing here, right? But the moon is exactly at the distance, right? 400, the distance is exactly at the right distance away from the sun, such that it appears to have the same apparent size of the sun, since the sun is so far on the order of 90 million miles away from the Earth. And basically, if every now and then, you know, the next week, right, the moon, right, is completely aligned, not only aligned on the rotation axis, on the plane of the rotation axis of the sun and the Earth, the line of the sun and Earth. If the moon was, you know, in some elliptical act away from that line of sight, then of course, you would not get an eclipse. So you need exactly the Earth, the sun, the Earth, and the moon to be completely on the same plane as well. Okay, and that's what we see in that picture. So it would look like a bird's eye view looking down. Once that happens, right, there is, the moon casts a shadow. And there are two shadows. One is called an umbra, which is sort of the darkest part, which becomes the path, what we call the path of totality. We'll talk about in a second. And of course, other parts where we actually can see some sort of partial obscuration. Now, there was supposed to be a video that would actually really show you how this works, but I don't have the video available, so let's move on. But this video will just animate just a coincidence of the moon just moving around the Earth, and every once in a while, you know, I forget how many years, Jan, for total eclipses.
For total eclipses, it's about once, a little less than once a year.
Okay.
But only on some certain parts of the year.
Right, right. And so this video is to show basically that coincidence, okay? But that does happen. Now, what I want to show, for some reason, it's not advancing, okay. So in 2017, yeah, in 2017, we had a total eclipse. And this is what we call the path of totality. This is a path where you get a total eclipse. Okay? And so in 2017, these were the states and the cities and towns that got to enjoy that. This year, it's going to be along here, as Angela showed, and Francine. And I will be on Friday. Where will I be on Friday? I'll be in Austin, Texas, to also play the eclipse. They wanted me to play, believe it or not. I'm always a token physicist that they invite to play music. I'm never appreciated for my physics. This is wrong. Okay? I protest. But since they pay my flights and all that stuff, best that you're hearing that I have to use any department money for this. Okay? And so that's kind of, this is another rendition that, you know, how far you need to be away to get 90% of the total eclipse and so on and so forth. Okay, and this was supposed to be a video that kind of animates basically as you, yes?
Since there's not a video, on one of the previous picture with the track,
Yes.
why is the one track wider than the other?
That's a good question.
The moon's just a little bit closer during this eclipse, it's just a little bit bigger, which makes the eclipse half a little bit wider.
I didn't know that. I'm the general relativity expert here, so now that's what I'm about to talk about. Okay. All right. So now, that's my little thing, you know, spiel about the eclipse and a little bit of the mechanics of it, and you know, our you know how important the moon is. The moon is eating the sun, right? And the moon is also important for life. And I want us to appreciate just the amazing coincidence of where the moon is placed at our time of existence. So I'm all about worshiping the moon god. Okay. So let's talk about Albert Einstein. So in 1905, Albert Einstein completed his theory of relativity. He went off trying to calculate things. A very key figure was a person named Karl Schwarzschild, who actually wrote a paper while he was dying from World War I. Right? Well, I think he was in the war actually, and he suffered complications from the war, and you know, but he wrote that paper where he found one of the first exact solution for a maximally spherical gravitating body, which could be used to describe planets, stars, as well as black holes. Okay, and this would capture the full effect of his theory of general relativity. I want to say a little bit about this theory. So everything that you thought you knew about walking through space and experiencing time is a fiction. It's some sort of approximation in terms of what you are experiencing right now. The real, what Albert Einstein revolutionized, without going into, if the chairperson lets me teach general relativity next year, then I can, the students here, we could
As long as
learn.
I don't have to teach it.
You can teach it too. In fact, I stick around for my next slide. I think you'll enjoy the next slide.
I will.
Okay, so this slide, the real picture is, you know how a magnet, you know, magnets can exert forces on each other without you ever seeing a magnetic field? Without the magnets actually touching each other? But you believe in magnets, don't you? Even though, right? You do this, it moves, right? Well, gravity, in a sense, the space that is in between gravitating bodies, Albert Einstein basically, his theory said, it's a field. It can walk, it can bend space itself, okay, and time. And the real picture of the sort of reinterpretation of what a gravitational force between two massive bodies are. Like, for example, if this is a very large planet and a moon, or a sun and a planet, is that this gravitational field, which is space-time, gets warped by the larger object, and the contours of that warping create a geodesic that allows this moon moves along the contours of this warp space. So we have to really turn around, revolutionize how we think about space and time, and this is the correct picture. And if you buy that picture, obviously Albert Einstein did, then you should think that really what's going on with the moon is that the Earth warps the space-time fabric, and the moon moves along the contours of that. Obviously, the moon itself also warps space-time a little bit itself, so it's a little bit more complicated than what I'm saying here. And those of us that do a lot of numerical simulations of gravity, like my graduate student Tots, appreciate this very well, don't you? Okay, and also you too. Okay, all right. So here's another picture I want to talk about. These are the seven sisters. I believe for those of you who are into the zodiac, I think you can see one of the eyes of Taurus. On this, I know nothing about zodiacs except.
Those are very stubborn people, man.
My mother was a zodiac. My daughter's a zodiac. My grandmother was not zodiac. All of them were Tauruses, and I can totally agree with that. Okay. So, if we have these stars, and you can imagine that there's a really, 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 really heavy object, like a sun, like a star, like a sun, right? And it's here, according to Einstein, the space-time around the star would be warped, and it would obscure the light. Well, Einstein's theory also said that if space bends, light actually will also, right, its trajectory will get bent along with the contours of the space-time itself. This is the prediction of his theory. He performed a calculation in 1911, okay, where he got the wrong answer. He went back and did it in 1950, and he got the correct answer, and he actually calculated that effect, and basically, a rendition of that is that here's the Earth, here's a telescope watching sunlight. If a star is actually here, and that light gets emitted from the star, it starts experiencing the warping of the space-time and gets to Earth. But some observer who doesn't know this is going to infer a straight line and see some apparent star location actually to the actual star location, and Einstein's theory would correct for this and actually tell you where it should be. Now, if you buy this, that means that if you go make an observation of those stars when the sun is not there, right, then you can compare the two pictures. And that's the strategy for actually confirming, or, and very importantly, saying that Einstein's theory is incorrect. So the point here is very important for students to hear this. The theoretical physics would be nothing without observations and experiment. I don't care how beautiful your theory is, right? Albert Einstein was smart enough that within, I think, 5 days, he was already calculating the perihelion of Mercury with his theory. Okay? So the challenge was now how to find this, how to actually detect this. And I wanted to show you that this is all these words and stuff. Here's basically the calculation. We could talk about that. And this basically is the correct answer in terms of the deflection of light. Okay. And for anyone that wants to do that, I have a group meeting later on. I'll probably call one of the students to the board to solve the integral equation. So in 19, this is why I'm bad with dates, 1990 maybe. 1990 to 19, there was a total eclipse. This all happened from 1915, okay? Albert Einstein had this correction. And Sir Arthur Eddington at Cambridge University, who was an observationalist, who was an experimenter, knew enough. He was one of the few astronomers that actually studied differential geometry. This is very important. He was one of the few people who actually built experiments that actually understood general relativity enough to read Einstein's paper and say, he's onto something. And he spoke to Fowler, I believe he was the Royal Academy, was some big dog in the Royal Academy. And they got together and decided to go look for and try to make a measurement, try to measure, take a photograph, very precise photograph. So they went on an expedition to Brazil and Principe Island off the coast of Africa. Eddington went to Principe, and they actually, there's a picture of him, of Eddington. Now this is actually important. This is during the time of World War I. And Germany, Albert Einstein was in Germany at the time, and Eddington was in England, and these countries were at war with each other. But it didn't stop Eddington, right, from reading Einstein's paper. And this is a very important lesson, right, about whatever, the importance of science, that science has to continue despite whatever politicians want to do. So here's a picture. I'm going to talk a little bit about Principe. So this is Principe Island. All right. This is the continent of Africa. This is the closest I've ever gotten. Well, I was once in Morocco. That's northern Africa, but in terms of, you know, where some of my ancestors came from to the Caribbean, somewhere in Sierra Leone, I believe. And just to show you, these are stamps of the country Principe. It is one of the smallest countries in the world, and so he's clearly celebrated there. And so the point that, yes, what I should say was that this confirmed, I should have something here. Oh, I don't have my picture.
You have
So-
your plane.
Huh?
You have your plane.
I have my plane. You're gonna like that story.
So,
So yes, Eddington and Fowler did confirm Einstein's theory, and then they reported this in a scientific meeting, and the New York Times picked up on this, and Einstein became an international superstar for the rest of his life, right, and remained such. Now you'd say, what does this have to do with me? Why should I care about eclipses anymore? The very same equations that I wrote down here, okay, these equations that I wrote down actually are roughly the same equations used for the GPS satellite system that your cell phones rely on. Okay? It's just you're looking at the temporal components of the field equations, but it's the same essence. Okay? The point here is that we never know when we do these precise measurements and look for fundamental physics, right? Einstein never dreamt that you would have cell phones, right? Using his equations, all right, to actually make GPS satellite work and make your whatever you're watching on TikTok or your phone. I don't know what these days. Okay. All right, now I want to use the rest of my time to talk a little bit about my own adventure. So this person is not an astronaut, okay? He paid for this. He's a billionaire. His name is Mark Shuttlesworth, and he is a self-made billionaire from South Africa who is like a physics fanatic. And, you know, at some point, we should try to get him out here to write us a big check, okay? Because he loved Einstein so much that he pretty much bought the island of Principe, okay? And so he reached out to me, don't ask me why. In 1919 was the 100th anniversary of this eclipse, and he wanted to have some big event, a big party for the country of Principe to celebrate this. And his idea was to bring the head of the Royal Astronomical Society and some other prominent relative people who work on Einstein's theory to fly, and unfortunately, well, that's not true. Two of them were observationalists, okay? So, you know, so don't hate on me. And the rest of us were theorists because we're cheap. This is he owns a resort on the island. This is a picture of a part of his resort. You put these are individual huts that he gave all of us. Here's a picture of Principe. Okay, that's Pirates Peak or something. And this is a plane. This is his private jet. He took us on his private jet. Okay, this is us. This is his assistant and wife. Okay, she's pretty cool. This is Laurent Friedel, who's the head of Pyramid Institute theory. Again, I'm not going to remember names. These are all prominent, astronomers, mainly from the UK, whatever the Royal Academy people. This is me. We landed on Principe Island, and as you can see, they put on a nice performance for us, and we were met by a lot of kids and people. And so this is a picture of me. I guess my hair started to get gray back then. Now it's more gray. This is a place that they put me to stay in by myself. I was wondering if there were dangerous snakes out there, so I didn't get too far into that at nighttime. The telescope was being used to look for animals that would try to get me. I'm a city slicker, so for those of you that know about me. You probably heard about the SCA. He's the head of SCA in Roy Martins. And these are various people. We went on a little boat ride. Obviously, I had to bring my saxophone along me. to scare away the dolphins or whatever. Yeah, as we were going on this boat ride, we took a trip around to the site where Eddington was at. That's why we went on this boat ride. It wasn't for entertainment, it was in the spirit of science. So we saw these kids with their own little boats, and that was pretty cute. It's like, I want to be that kid. Why did my parents bring me to this with Winters? Here's some other kids hanging out on their boats, you know. Who are these weird people taking pictures of us? This is us, probably young will recognize some of these faces. This is us now. Now, Shuttlesworth got mad at me because he wanted everybody to wear what you call this, a tuxedo? And it was a big deal. This was a big deal to this guy. He's planned for 20 years, and one day, the 100th anniversary, fly out these physicists, right? And he said, we're gonna go now to, I bought the place where I bought it. You guys are gonna go there, I wanna get a nice picture with all of y'all in tuxedos. And unfortunately, I forgot to bring a tuxedo. And he was not happy about it, but everybody else is looking nice in it except me. This is me and my buddy Laurent Friedel. This is me and some of the kids that were hanging out. Notice they probably wore a t-shirt that had gravity on it. Right, it was a big deal to the people of Principe, that's the point. It's like a big deal that this theory, they feel a part, and rightfully so, ownership of this major discovery. And a big part of their country is a celebration of Einstein and his theory. This is us now having, dinner, secret space, I don't know what the heck that is. Some interesting looking bird. Nice little view from the plane. So what's the lesson here? Hey, every now and then you get to fly in a private jet with a billionaire. That's right. And this is what the New York Times looked like back in 1919. Okay, and here it goes. The end of science, more or less, a god. I don't even know what the word god meant. Somebody. Ariel, what does a god mean?
It means amazed, shocked.
Okay, I'm gonna.
Jaw-dropping.
Jaw-dropping, all right.
More or less.
It sounds negative, like a god. Okay. Einstein's three triumphs. Okay. He became the star. So both the expedition of the island of Principe and Brazil, it not only crossed geographical borders, but also cultural borders. The world was at war. And the reason why I think, in 1919, this made Einstein a international superhero was also the war ended, and there was a feeling of hope that, look, these two warring countries, these scientists transcended that and managed to make this big accomplishment, right? And thank you for your time. That's it. Any questions, comments, corrections?
I have a question. The observations that they made, they had to get in two different spots on the Earth to see the difference between the bend?
No. One was incorrect, I believe, and one was correct. Which one was it?
Yeah, so it was just to give more chances for clear skies.
That's it?
Yeah.
Oh, okay.
Because they'd taken pictures 6 months before, so there was comparison between the old pictures at each site with each camera.
Is there anything crucial that I may have missed that's worth mentioning? Yeah. Okay. Any more questions or comments?
Are there any tools from Eddington's time on the island when you were saying there, like artifacts from?
Yes, there were. Yes, there were. Yeah, they kept some remnants of something, but my memory is shot.
The film is still at the Royal Society. That's where you can go and make the measurement yourself. There's been some, the photographic film contracts with age. So the measurement is slightly different now than it was.
But I think maybe you can comment on is the precision. I mean, apparently I didn't have the bandwidth to explain it, but somehow how great of a measurement it was, right?
The splitting is really small. And so it was
it's like holding a dime a mile away or something.
They had to measure many stars and take the statistical average to get the precision they needed.
And it wasn't one star, it was many stars. Yes,
I mean, it is instructive to look at the photographs. They are available. that they took, personally I would say it was debatable that they actually had the necessary resolution in those plates to do what they claimed they did. It's when you actually calculate what the shift would be, and then you realize what it would mean on the plates that they had. It's staggering. And you're absolutely right that they were looking for statistical effect across multiple targets, but you're still only talking about, I don't know, 6 or 8 clearly resolved stars in a region where there would be any measurable shift at all. And I'd love to have the time to attempt to do
a recreation of that
analysis.
Yeah, that would be really cool.
Of the thing, but when you actually just physically realize how small the shift is relative to the plate resolution, and the challenges associated.
If you were to apply your standards today, in terms of like measuring very faint signals, right, which is what you do, to the state of the art back then, was it impressive what they did?
Obviously, it was exactly the right experiment to do.
Mm-hmm.
As you related, there were significant challenges, just as there always is with weather, and getting the right shot. I think it's very instructive to get a sense of just how ambitious the measurement was. Go look at the plates. You can get access to them, and look to see, and then make sure you work out how subtle, physically on that plate, how subtle the difference between a Newtonian and an Einstein deflection would be. I mean, factor of 2, but just get the magnitude.
Yeah, that's something I didn't mention.
Figure it out. I mean, it's a lovely opportunity. Were they skewed by the fact that they knew what kind of result they wanted? One would have to suggest that that was very much in their mind. It was such a beautiful theory, and the method, as you've said, of verification was very compelling. Is there a particular experiment you would have said did actually nail the deviation that came later?
Sure, the radar ranging of Venus was definitive.
Right, and that was on until the 50s. So yeah.
But I will say that there has been a reanalysis. So a group did go through the plates again, and they did not get the answer that Eddington did, but they got an answer that was inconsistent with Newtonian.
It was in the right direction.
It was in the right direction, right? It was 1 point something effective at the limb, 1.3, 1.4 instead of 0.85, which was the Newtonian. The actual value was right at the edge of error.
What were the error bars?
Yeah, so the actual value is right at the edge. It was like 1.5 sigma off.
Yeah, which is not a verification. I mean, that's not even close.
Well, except the Newtonian was more than 2. Right? So the idea was it was more consistent.
Oh, sorry, I don't know what you mean by the 1 point.
1.5 off the actual Einstein answer.
Oh, no, that's not the thing. It's
the Newtonian that was more than 3 sigma.
You're saying it was, they estimated 3 sigma incompatible with the Newtonian.
Yeah,
wow.
So again,
that's damned impressive. You please go look at the photographs and make sure you bother to do the calculation for what the deviation would be.
Be a nice qualifying example.
You have that reference.
I have one more question. You have that image up, that was just up there. Of the moon.
The moon.
With the sun behind it.
Yes.
Is there a way now of measuring the bend of the light from the sun to the earth by the moon?
Well, yeah, that is, I don't know the answer to that question. That's more of a question for Jan, actually.
If it was a total eclipse, is it possible to measure it?
The bending.
Because the light would be going much closer to the moon because there's no atmosphere. And that light would be measurable if it had a bend that the moon had a magnetic effect on it.
So the problem is that the size of the effect goes as m over r. And the moon is 1 million times, more than 1 million times lighter. So the sun effect is an arc second. The moon's effect is something like 1,000 times smaller.
So Jan is talking about, this is a correction. Notice that it goes as 1 m over r.
Okay,
So
they wouldn't see it.
Yeah, so
You wouldn't have the equipment now.
You wouldn't see
to
it,
be able
but
to measure.
we use something called PPN. There are other ways of testing exactly what you're saying, right? They're post-Newtonian approximations, and that's something I'm very familiar with. All right, yes.
This
Which
might be
basically these
this might be a
questions.
question for you actually, or for the cultures that like you talked about in ancient China that they had an essentially animalistic view of what was going on, that there was a dragon eating it, and yet they still had time to come up with drums and things to ward it off, right? So, like, on what basis were they making that prediction?
Remember, it takes about an hour, from the first contact for the moon to completely cover. So, yeah, so there's
They were
enough
ready for
time to
Time to
stop
run home and
jumping
get your
around
drums.
and doing stuff.
Okay.
It's very similar if a warring nation comes after you, you gather the stuff quick and you go for it.
And I guess I have a follow-up question that's sort of related. Is that, I there was a time in my life when I spent a lot of time with the physics of bodies in space, and that math makes sense to me. What I've never really understood, and where I struggle, maybe this is something is the math from a terrestrial perspective. The math that says how do I chart out the path of the eclipse. Is there a reference that you like for, suppose I want to figure out the path of the next one. I don't even really know what the independent variables would be for the calculation. And
Yeah, I would.
is there a name for that branch of?
I would say our friends in Deeps, they pay attention to things like this, right?
But also, it's just part of the same celestial mechanics that people do to figure out the positions of the stars. The complication is, the moon's orbit precesses, and so you have to put in all those things, and now computers do this for us.
But if somebody was doing this in ancient Greece, then there has to be some kind of practical.
So in ancient Greece, they were just working on the coincidence that the alignments, because these things have a particular time scale, they figured out there's an alignment that occurs every 18 years and 3 months. There are many such families, but for each one, they're linked by this 18-year period. And so they could predict when an eclipse would be, and they knew that it was a non-integer number of years, so they knew roughly where on Earth it would be. Getting the tilt of the orbit to figure out exactly, what the shape of the path was not so. But the path of partial eclipse would be big enough that they could verify they could get a partial eclipse.
We have a question from us.
Yeah, so I'm not sure if this is more of a question for you, Professor Alexander, or for Professor D'Antonio, but we made a statement earlier in the talk that the moon is at a perfect distance that would allow for the existence of total eclipse to occur at all. However, we do still see the annular eclipses, or the rings of fire, that happen every now and then. So, what are the conditions to produce that type of annular eclipse instead of total?
I mean, that is the interesting coincidence, right? We are at the right distance where the ellipticity of the moon's orbit can move you from one to the other. 500 million years ago, there were no annular eclipses because the moon was always too close. In a few 100 million years, there will be no total eclipses, and so there will only be annular eclipses. We live in this, depends on your definition of special, right? It's several 100 million years worth of special time when you get both.
Cool. That is cool.
So is the moon gonna wind up in the sun?
No, it'll still be bound. The equilibrium position orbit further away, 50 days.
So it won't escape from?
No, it doesn't have an escape velocity.
So
Any
it gets
more?
elliptic.
Yeah.
Before we all leave, you've probably seen the huge black tent in the lobby.
Mhm.
Inside is a entirely student-built, student-calculated, and student-assembled dynamic model that's going to explain how and why these eclipses happen. So hopefully by the end of today, the motorized component will be up and running. It's free and open to everybody.
We'll get an email.
It'll be open in the weekends as well.
But it's open right now in a static form if anybody wants to see it.
So, if you have young kids, if you know young kids who like big shining lights and huge models of the Earth and moons.
It's kind of like a disco, basically. Is that what you're
It
telling
is
me?
like it's an astronomical disco.
You'll feel very at home.
All right, thank you everyone so much again. And the rest of the staff that helped make this happen. Okay.